Okay, all right. So I woke up this morning and I realized I'm a little bit frustrated with the progress. I actually did, aside from streaming, get pattern matching with sequence patterns to work when they're named, but I didn't get it to work otherwise. But what I thought I wanted to do today is actually just I have about an hour, maybe a little bit more than that. And I just want to go through and sort of condense down everything that I've learned in building this symbolic programming language, and describe exactly what it is from scratch. We don't need this. This will be good to have so that we can test our behavior, because effectively we're making our own Mathematica. So what I'm going to do is I'm going to start from a blank Rust project again. So I'm in my whatever. I'm going to say cargo new cas 4. Then I'm just going to open up that thing. And once we're here, we're going to wonder, okay, how do we start? What does it even mean to have a symbolic programming language? And I guess the first thing that anyone would probably think of is, what's a symbol and how do we represent it? And so this gets to the idea of expressions, which is a natural thing in pretty much every programming language, is that you have some expression that represents doing some computation. And so we need a way to represent expressions in our programming language. So what we're going to make is an enum. I'll just call it enum expert. And actually, I'm going to disable, hold on, well, I always hate this, but whatever. I'm going to disable Copilot because I think it might make things a little bit annoying. Just disable that for right now, just so that we can really figure out what it is we're doing. Okay, so what do we need to put in this struct? Well, we probably need a symbol type, and then so let's just say we have this. We can make an expression. Let s equal this, or let's just call it x, because we're talking about a symbolic programming language, and algebra is very tied in with that. It's not really that important. Let's just try to run it. Interesting. So let's try to do this. Let's see, does that work? We need to add this, derive debug. That's just a Rust random implementation detail. That's really not something I care about. But, okay, so all we have is symbol. But we want to store some data in there, like the fact that two symbols may be different. So we're going to add the fact that we can store a string in there. And so that means that we can say that this is a thing called x. And then now I'm going to make a slight change. Let's call it sim. But now that we've introduced that it represents a symbol, I'll call this symbol just so that in the VOD we know. And I wonder if I can make this take a stir. Can we do that? Yeah, I guess not. Let's just make it take string. And we'll do this, which is fine. And so now, when it prints out, it'll say sim_x. So that's good. So now we have what are the atoms of our symbolic language. So, but we need a way to represent expressions that are compound, that may take multiple symbols and do things with them. So we're going to introduce the fact that expressions are naturally tree-like, and we're gonna introduce I'll call it what's a good name for this right now? We'll call it list for the sake of expediency, as if anyone's seen my older streams, this is what I have in my other languages. And what is list? List is basically going to take a vec of experts. So now we have this compound structure where we can say let L equal expert list of vec of x and x. And I think I probably have to clone these guys, but we'll see. Right, clone, and we will get to, oh, and I have to now do this thing where I do clone, right? Okay, and now we're able to copy expressions, and this some Rust macro learns, okay, I just recurse and I copy everything and I copy everything. And so now we should be able to print L, which has 2 X's. That's great, but what does this actually mean? Well, it turns out what this actually means is calling the function x with itself as an argument. So this is actually what this operation means. If you're to think of the first argument of any list representing some operation. So what we could do here is we can make this plus, and we can make 1, so we'll call this plus, we'll call this 1, and we'll just put the character 1 in there. And so then we'll say plus, and then we're going to do this. Or actually, we don't need to do that, but we need to do 1, 1. Okay, and then we're going to print this list. And so now we've started with the most sort of fundamental thing that we may want to do in our programming language, which is 1 plus 1. So that's pretty good stuff. And we'll get to actually how to evaluate this, but that's not the purpose of this stream. The purpose of this stream is to clearly understand what it means to have patterns and think about programming as acting on the structure of the arrangement of symbols and their values and transforming them into something else. So where should we go from here? Well, one thing that we could do is we could, I guess the simplest way to think about some sort of pattern or transformation rule between expressions. So think about the idea that plus 1, 1 ends up going to the value 2. How do we actually do that? Well, we could store some sort of rule just in this hash map, in this map that says anytime that this is our list, or if we see that expression, then we can apply a rule to get down to this new thing. So what I will do is I'll say let HM, or let's say rules, let rules equal hash map, and we'll add that to our thing up here so that we can use it. And we'll say this takes an expr and returns an expr. And so I think I don't have to do that yet. I think it will infer that in the compiler. And so right now it'll say expected semicolon. Oh yeah, it just expects type. Oh, I need a colon. Alright, so that's all good, and it says it doesn't know the types yet, but that's fine. Let's just add a rule to this, and I think we need to make this mutable. And we're going to say let rules.insert, and we're going to say if we see L, and we're going to clone it because otherwise we pass it in there, we're going to return the symbol, and I'll do it here. I'll say let 2 equal expr sim 2, and then I have to clone the string because of how the memory thing works, but that's more of an implementation detail, of course. And let's see what's wrong here. Oh yeah, 2 string, that's good. And then we're going to say 2. Now, the simplest possible thing. Oh, right. And so this is an important thing that I forgot to bring up. If we're going to have some dictionary that allows us to look up, given an expression, how we should transform it, then we need a notion of expression equality. We need to be able to say, hey, does L actually exist? Does L actually exist in our hash map? And the only way to do that is to have some notion of equality. Now we could write this ourselves, or we could do this thing where we derive partial eq and eq. And I don't know a ton about these, but I know that eq allows us to say L equals L. So now we should be able to do, and we have to clone these guys. And there'll be clones all over the place, but who cares? from derive. And so now if we run our little program, we are going to need to, let's see, hash. So we also need to be able to hash it. And that's another one that we can just derive. So luckily, since our expressions are so simple, the Rust compiler is able to figure this out. And it finds out that L is equal to L. But if we did, let's see, is L equal to 1? We get false. So that's good. So we have some notion of being able to say, are these two expressions equal? And that just amounts to basically saying, are each of the atoms the same and in the same order? But so now we're going to say this insert rule, and we're gonna define a function that just says, well, before we do that, let's just try to see how we could apply a rule. So we'll say let new, let's say, let answer equal rules dot get, and we'll say if let sum. This is a Rust thing, and it's basically just saying if this is in the hash map, we are going to look up L. We're going to say print found a rule for, and we put L in here. Do this thing. Let's forget this. Why does that not work? Oh, we need to borrow. Okay. Right. That has an answer of else no rule found. So since we inserted this, we should be able to say, okay, we have the answer. So we'll say found a rule for 1 plus 1, and the answer is 2. And right now, this is already, I'm sure everyone should, be like, this is a terrible way to do things. Because we need an infinite number of rules in this hash map to be able to just do plus. And we're probably not going to actually do plus, I think, in this stream, because the more general thing is how do we represent patterns? And patterns are, let's see, how do they define patterns? Patterns stand for classes of expressions. They contain pattern objects that represent sets of possible expressions. That's a very good way to describe it. When several pattern objects occur, yeah. So anyways, the point is, how do we do something like we do in a traditional language where we say, function my plus a of type, what is the I64, a of type, or b of type I64. Like, how do we do this where we are saying, okay, this stands for some class of it? Some class of expression. Well, we want to be able to say that there's some rule that matches that when we try to do this lookup in a more general sense, when we look at this expression for 1 plus 1, do we have something that is defined there? And of course, it's natural to do this on a more general level than just a specific rule that is up to equality. So we're now introducing the idea of basically a hash map get on a more general level than equality on expressions. And so the way that this is represented is with a special name. So we just start to introduce names that have special meanings. So plus would naturally be plus, but we introduce the idea of a blank symbol. So let blank equal sim, and we'll do expr. And then this is actually a list. So we'll call this a. And what is a good way to describe why it is we would want blank to be a one argument function? So in Mathematica, the quick and dirty way to think about patterns is that blank, this figure, can stand for exactly one expression, but it matches any expression. So if I have f of a, of b, of c, of d, some big expression, and this can be nested and all that jazz, but we have this fundamental thing that we're going to try to implement on our own in our own little mini language here, and it's basically this match function. And this match function is this hashmap.get on a more general level that looks at these blanks and these patterns that stand for not just exact equality, but classes of expressions. And then how do we sort of say that these two expressions can mean the same thing? And so this returns true. And one thing that I don't know if people that know Mathematica know, this is super cool because true is actually just a symbol. This would be the equivalent of us writing, let's say this is true. So our true, oh yeah, we probably can't name it that. My true, and it's just calling it true. So we already have Boolean data types just in the fact that we've started a convention that this specific symbol name has meaning to it. And it's a very cool idea to have a general way to construct your own little system of logic just by saying that this symbol has this magical incantation that we know to be true. And it makes code really readable. I really like it. Two-string. Okay, but one thing that I wanted to, as a, I guess what I'll say is that at the end of the day, every form that we look at in this notebook will have the exact same structure with some caveats in that they have more atom types, like they have like a number here, for instance. And we could do that, but for right now, for our purposes, it's fine to leave one as not really a number because we're not really going down that rabbit hole yet. But the point is that every expression that I type in here on the stream and forever is going to be able to be represented with this kind of expression type where you have a tree. And so the question is, what the hell is this blank thing? Well, we have this handy thing called full form in Mathematica, which allows us to look at the underlying expression form. And you can see here that the way that blank is represented is as a zero argument function. And it turns out that you can actually there's an optional one argument function for this, and we will get into that. But for right now, we are just going to look at this. Okay, so it turns out that this ends up being a list because remember, lists represent the first argument as the operator and the rest as the arguments. So what we're going to say is this is a blank sim, and then we're going to say let blank equal expr of list of blank sim. And I guess we'll clone it. And so now what we want to do is, and we'll see naturally that because we take the list. And one thing that I'm going to do to make things a little bit more expedient, we're going to define a function called sim, and it takes a pointer to a string, and it returns an expr. And all it does is it does expr of sim of s dot to string. And this is just convenient. So now instead of writing this whole thing out, I can just write sim blank. And that makes things a little bit nicer to read. But this is just a simple helper function for, whatever. So now what's the value of this blank nonsense? The point is that we want to be able to say, rules.get of well, we want some way of we'll call it match. We want some match. We'll call it my match that takes some expr and some other expr and returns a boolean, returns true, a symbol of true or false. But that is more general than just using the implicit equality that we have when we do this derive eq. So what we're going to do is we're going to try to implement this functionality, and we're only going to start off with the basically the fundamental idea that if I give any expression in here with this one being blank, then it has to be true. So basically anything with blank goes to true. And it would probably be good to look at why is blank a function in Mathematica? I know sort of why. I guess what we could do is we could try to assume that blank is not this, and it's just a symbol, and see where we break down when we try to do stuff like blank of h, where this goes to blank of h. But all right. So let's try to write this function, and yeah, we'll do everything from scratch. I'm good with that. Okay, so it takes an expr, and it takes we'll call this the pattern type expr. So they're both expressions, but now we're basically saying that this can have these special symbols called blanks that can match anything, and then we're going to return a boolean. So now we're going to match on. All right, before I write anything, let's just think about it. What we can do is we can actually match on both things, which is a very handy thing. So we can match on expert and pattern. Does that work? Right. Okay. Wait. I think I can just do this. Okay. So now if we see an expr sim of E and an expr sim of P, then what does this mean? This means that we have two of these guys. We have two symbols. And if you have two symbols, the only thing that you can do is compare their equality. So this is going to say E equal to P. So that's all we can do here. So that's like saying, does one and one match? So we can add a test case for this already. So we're going to say let x hat and expected equal vec here, and we're going to say this is going to be sim of 1, sim of 1, and true. Okay. Does that work? Oh wait, I need to make this a tuple. I think that should be fine. But anyways, we'll do for x at expected in, oh yeah, no. Test cases. What we're gonna say is, what do I do here? Assert eq my match of x hat is expected. And I think yeah, I think I have to do this to do. Cool. So now we have our very first base case, and we're gonna run our code. And so it passed. So and I'm gonna enumerate these. I think I have to do .iter.enumerate. And then we're going to do print line testing case I. Okay, cool. So now we can finally move on with our life because this is boring. And then what's going wrong here? We need to clone. What's wrong with this? Okay. So this would, so if we change this to false, just to show everyone. It says, all right, well, we try to compare true with false. But this is what we want. And we want another one of these. Okay, but now what do we want to do? Now we want to say, I want these to be down here so I can copy them. And I want to say that 1 and blank. Should we do this where blank is just a symbol? I wonder. What's going wrong with commas? Yeah, that seems like a good idea. So I'm reverting what I said about making blank a list, and it's not going to be a function or anything. It's just going to be this symbol blank. And what we'll hopefully do is we'll see how this breaks down. Hey, what's up, dude? Oh, I didn't see your comment, man. Damn. Okay. So what we're going to do is change this now. And we're going to say if p is equal to this blank, return true. Else, and we're going to return this thing. And I don't think we need these return statements. I think we can just do that. So now what we're going to do is we're going to say, oh, this is so annoying, this formatting thing. We need to make a whole bunch of these. So I'm just going to add those so that, yeah, now I format and it's fine. If I comment these out, does it still? Okay, cool. So now what we're going to do is we're going to test again. And 1 is obviously not equal to blank. Like the string blank is different than the string 1. So these should fail if we did this. But since we're special casing, we're saying if it's blank, just return true. Cool. So we expected true, and that's all good. Now we want to add the case where we have sim key expr list keys. And so as we're constructing this more general sense of equality or some sort of matching where this can be a broader class of expressions, and we're asking, does this pattern, can you fit it into expression? What does this case actually look like? This case would be like if you had just some random x and you're matching it with yeah, this is probably the simplest case. And is there any circumstance where we want this? I would say no. I would say this is always going to return false. And when we end up reverting this idea that blank can only be a symbol but is actually a list, then we will go back on that, but that's fine. Okay, so now we want to add a test case for that, and we want to say, we'll just say, what we'll do is we'll do, oh, I guess what I should say here is the reason why this case, I won't write it out. The reason why this case should return false always is because when you think of this or this, however you look at the character level representation of what this expression actually means, when you have a list, by convention, we're saying the first element of the list is the function or operator. With respect to the rest of the elements in the list. So when we say, is X matching, this? Well, they're different things fundamentally. One of them is a zero argument function, and the other one is just a symbol. So this should be false. So let's do that. We'll say expr list and we should expect this to be false. So let's just run it, make sure that nothing goes wrong. Nothing goes wrong. And actually, I'm gonna do this so that once it's built, it should just be fast. Cool. But now we want the good stuff. Now we want to say, does a list match? We want expr of list ease and expr of sim p. And we're going to have the exact same case as we had here. We're going to say, if p is equal to blank, return, or we're going to say true. Else, false. That's it. And the reason for that is that there's no case when if we flip these guys, if we say x like this, and this is just a symbol, that this should ever be true unless x is equal to our special symbol that says, you know, it says it's like our wild card. So let's add a test case for that. And remember, this thing represents calling the function 1, which would be like 1, which, maybe doesn't make much sense, but for the purposes of thinking about the structure of expressions, I think it does. So we're going to... and then we're just going to say and this should be true. But then if we have this with just our sim1, this should be false. So let's run our thing. Cool, so none of them failed. This all does what we expect. And I'll write this out. I'll say goes to, I'll put in 1 equal to 1. So this is sim arm. Then here we have sim arm with blank. This is sim list goes to false. And this is, and what we could do, well, I'm not going to get into that right now. And then this is also list sim. Oh, we should do this one first. List sim with blank. So all of these ran. Now the real good one is the list arm. E is for the expressions for sim or list keys. And now what is it that we want to do here? Naturally, we basically just want to so what does this mean? Since this blank symbol that we have is fundamentally representing one expression, then we can start to make assumptions on the length. So if these two things are different lengths, so if we had different lengths, meaning like FAB, which is, I'll write it like this, FAB, and we were trying to match that with F of blank, well, these are different lengths because this blank can only match to this A. So these should just default to false. So if these are not equal, return false. Okay, so now we know that these are the same length. So what we're going to do is we're going to actually say for EP in es.zip, iter.zip, and we're just going to recurse here. That's the simple thing. We're going to say if not my match of EP, and we might have to clone here, but we'll see, return false. And then if we get to the end here, we do true. We got a clone. And this is, I'm not worried about efficiency right now. All we're trying to do is understand the concept of pattern matching as a more general form of equality. And so now that we've done this, we should be able to, and I'm going to define a helper function called list. And it takes of expr and it just does expr list then I'm also going to do one that's I'll do that. This takes a vec of pointer string and returns expr, and so what is it? Iter.map s sim s collect. This is all just not. I feel like this is all literally just Rust's nonsense, but whatever. Then we can call list of x's. Let. Cool. So now we have this convenient, handy function where I can just sort of write what I want, and I don't have to bother with all of this syntactic garbage. So what should our test case be here? Well, we want to test first that list stirs to list of we'll say F, A, B, and so I'll say let left hand side, do that for right now, and then we're going to copy this over right hand side. Oh, one second. Yeah.
Come here.
Yeah. Let me look at the Uber prices.
Huh?
$18. That's not bad.
Can you wear the little green sweater?
Which one?
The one that's like kind of striped.
Oh yeah, the farmer one.
Okay. Yeah, that one.
That's a shirt though. That's not a sweatshirt.
Not a shirt.
That's a shirt.
It's a sweater.
You put a shirt on under that?
Yeah.
What?
Okay, don't. Just wear the sweater.
All right, but then I'll wear my sweatshirt.
No, I'll give you a flannel. Your sweatshirt stinks.
Yeah, fair. Okay. Wait, should I leave now?
Yes, please.
Shit. Okay. All right.
All right. Bye.
Bye. Damn, I gotta leave already. Okay. Well, let's just finish this last part. So what we want is we want the case where this blank goes to false. So we're gonna say, let me move these up to the top so I can use them in my test cases. So we want left-hand side, right-hand side, and we want this to be false. But then we want this of vec of f blank to be true. So let's just try to run this and then I have to go. What happened? Let's do it here so that we don't. Cool, so everything passed. So now we have this idea that blank can stand for any one expression. And we've written this pattern matcher in, and it turns out that you can actually write this in much less code if I'm smarter about it. But I guess in the next stream, maybe tomorrow, I will get into introducing blank as a function that can take an optional first argument, which allows you to do the following. match Q of this and this being false. So basically saying this, actually let's write it as blank F or blank H or G, what did I call it? So basically saying, does the first argument, the function name or operator, or however you want to think about it, match this first argument? So in this case, F is equal to F, or matches F, for instance. So what happens if we put a blank in here? That's not true. Interesting. Oh, I think if I I think actually the reason why, if you look at the blank thing, the documentation for blank, the head in H cannot itself contain pattern objects. That's why this doesn't work. So we won't be doing that either. But anyways, we'll get into this idea that we're going to we're going to switch from thinking about blank as just a symbol that matches any wildcard to something that can optionally match a list conditionally based on its what's called head in Mathematica terminology. So I feel like this is a pretty good start. It's like 100 lines of code that gets you started with blank pattern matching. But we're going to extend this to the all right, I gotta go. But the idea that we can actually do sequences that can stand for, this is a good example, where there's just 2 underscores here, and if you give it this thing, then it looks at the length of what it matched. Yeah, so you see here that X, Y, and Z turns into a list that gets matched, and we say 3. But since, all right, that's a good stopping point. I think that this is a good piece of code to study, to think about how do you start building a symbolic programming language.